Hey Algebra students, this is a tutorial where we're going to walk through some of the questions that come to you in checkpoint 16. So as a heads up, before we jump into these questions, they might be rearranged, so just make sure that you're looking at the same problem that I am at. So in this problem, it's given us this type of function and it gives us a list of information and we ask to find which is true about this given function. We are asked to find the zeros, the x-intercept, and the y-intercept. So first things first is that I have gone into Desmos and I have graphed this function. You are always welcome and encouraged to use any tool that you want, a calculator, including a graphing calculator. So here I have my function. I can graph that. Just sometimes seeing it, especially if you're like me and a visual person, seeing the actual function is really nice. Also, as a heads up, as I graphed this in Desmos, I needed to adjust what I saw in my graph. So for example, if you looked at the y values, those y values are really big. They go up to like probably 60 and negative 70, but the y's were still, I'm sorry, I had that backwards. The y's are really big, whereas the x's are not. So what I did is that I just adjusted those over here. I needed to see more up and down, so I made my y's really big negative number and a really big positive number, whereas the x's, I didn't need to be super zoomed out on the x's. Okay, so just, again, we'll come back to that graph, but looking back over here, if I'm looking at this function, first I'm noticing that the form that this function is in is intercept form. It is called intercept form because it is really easy for us to identify those intercepts. And by intercepts, I mean x-intercepts. So this is where it's crossing the x-axis. By definition, to cross the x-axis, a coordinate needs to have a y value of 0. So this is where I'm going to replace the output with 0. And I'm going to solve for each individual input as it's factored. And by that I mean I can now pull apart each individual factor, set that equal to 0, and then solve. X minus, I'm just going to write 0.5, x plus 2.5 equaling 0. So here I'm going to get my x-intercepts at 2, 1/2, and negative 2.5. So what does that mean? My x-intercepts, I can have an x value of 2, but that is occurring when the y is 0. So I'm going to write that as a coordinate. X is 2, y is 0. My other one is at 0.5 and 0. And then my third one is at negative 2.5 and 0. Likewise, these are the zeros. Notice how I kept on saying 2, 0, 1/2, 0. So these are, the x-intercepts are just written as coordinates, whereas the zeros are written as just the x values. So if I were to go back to my my Desmos graph, I should be able to see those here. So again, x-intercepts, they're crossing the x-axis. Desmos does a really fantastic job of finding those for us very easily. We're seeing, again, all of those coordinate points, x value of negative 2.5, 0, 1/2, 0, 2, 0. Again, it's all tracking back to what we just found. Now, y-intercept, visually on the graph, very, very easy to find. Here's my y-axis, y-intercept, there it is, 0 and negative 5. The y-intercept is not super easy to find in this form that it's in, because again, this is intercept form, and as the name implies, it's really easy to find the intercepts within that form. So in this case, this is where I would go in and graph, and I want to make sure that I have that correct. Yes, negative 5. So y-intercept is at negative 5. So here's what we're looking at. Again, those zeros, we've identified what those zeros are. x-intercepts, we're taking those zeros and writing them as coordinate points. And then we have that coordinate point for the y-intercept. Beautiful. Okay, number 2 is asking the exact same for us to find the exact same information. We have a new function here, but as we can see, this function is written in a different form. This is not in intercept form. This is just in standard form. So same thing, I already had this one plugged in here. So here I have this one graphed in blue. Visualizing it, I can see where it crosses those x-intercepts. I can find those x-intercepts by seeing where it crosses those x-axis. So I should get a -3, a -1, a 0, and a 3. So again, oh gosh, I don't know if I can remember all of that. X was -3, -1, 0, 3. -3, -1, 0, and then 3. Okay, but x-intercepts, we can find those just because remember y has to be equal to 0. But let me show you how to do this algebraically. We've done this graphically by looking at the graph, but we can actually solve for this quite easily looking at this function and then factoring this function. So we know to find those x-intercepts, the output, a lot of the times we think of y, but this is our output. It has to equal 0. So I'm going to start by just replacing that with the 0. And then as I'm writing this, I'm noticing that all of these terms kind of have something in common. Every term is an even term, like 2, 2, 18, 18. And then also they all have x's. So I'm going to factor out what's called the greatest common factor. It's just what they all have in common. And in fact, I'm going to pull out a -2. And this is just a personal preference of mine. I really like it when my leading coefficient is a positive. It just makes my brain happier. It's easier for me to factor when I have a positive number there. So I'm going to factor out a -2x. So when I do that, -2 divided by -2 is 1. Okay, that kind of goes away. X to the 4th, if I take out one of those x's, I would have 3 x's left. So same thing here. Negative turns into a positive. I would have an x squared. -9x minus 9. So again, I divided every one of those terms by my coefficient. So what the benefit of doing that is that now I can look at just this piece here. And again, I'm looking at this piece and I kind of am seeing two different pieces. This piece. I'm seeing two different parts of that entire quadratic that's left. If I look at each part, they kind of have things in common if I grouped them. So in my first grouping, I see an x squared that is in common. So if I factored out that x squared, I would have an x plus 1. So again, that's just looking at that first grouping there. And I'll try and color code this. So if I looked at that other grouping, both of these have -9. So if I factor out that -9, I'm looking at an x plus 1. Okay, and then all to remember, we still have that -2x that is still multiplying with all of this. Okay? And then now, as I'm looking again inside my parentheses, I'm seeing something that is in common again. I'm seeing this x plus 1 and this x plus 1. So if I factored that out as a GCF, what's left? Well, if I take out the x plus 1 and this blue stuff, I'm left with that x squared. And if I take out the x plus 1 and the green stuff, I'm left with the -9. And again, trying to color code everything here because if you're a visual person like me, it just helps my brain space. Okay, and then again, looking here, -2x, nothing to factor there, x plus 1, nothing to factor here, but x squared minus 9, hopefully you're recognizing that as like, oh yeah, that's a difference of squares. So this is an x plus 3 times an x minus 3, and again, get my colors here. Oop, that's not the right color. X plus 1 and then this negative 2x. All of that is equal to 0. Okay, now we can say that we need to pull these apart just like we did in that last one. We have all of our factors here, so if I pull each one of these factors apart to set this equal to 0, x plus 1 equals 0, x plus 3 equals 0, x minus 3 equals 0. X is equal to 0, x is equal to negative 1, x is equal to negative 3, x is equal to positive 3. So there's how I manually find all of my zeros. So then to write them as my x-intercept, I would have, kind of depends where I look, but my first x-intercept was at negative 3, and that occurs when y is equal to 0. Negative 1 when y is 0. Then 0 when 0, 3 with 0. You kind of get the idea there. Okay, y-intercept. Again, very easily to visualize that when we look at the graph. Y-intercept is occurring at the same as an x-intercept, which is 0, 0. So y-intercept, very easy to identify visually, 0, 0. It's also very easy to identify when it is in standard form. The standard form, the y-intercept is always going to happen when x is equal to 0. So remember, x-intercepts happen when y is equal to 0. Y-intercepts happen when x is equal to 0. So that means if I evaluate this function at 0, so I replace all of these x's. Oops, that's supposed to be 0 plus 18 times 0. This goes away because that's a 0. This goes away because that's a 0. This goes away, it's a 0. It's a 0. So what do we get? F of 0 equals 0, which is 0, 0. Okay, so hopefully we're tracking here and we get the y-intercepts, x-intercepts, zeros, and y-intercepts. Okay, moving forward, the third question that comes up, we are referring back to that same intercept form. And now we're looking at different types of information that we can look at, which is positive intervals, negative intervals, relative maxima, and end behavior. So this is where I'm going to look back at my function. So we're looking at the intercept one. That's the one that I had in red. And first, let's look for positive and negative intervals. These are kind of related. So positive and negative intervals happen, I want you to think about as if this was like a hiking trail of some kind, and you are walking along the graph. So if you are walking along the graph, starting on the left, moving to the right, reading the graph left to right, just like we would read in English, which direction would we be going? Well, I'd be heading down, right? We'd be heading down until we meet kind of like this inflection point that's down here, and then we'd be going up until we kind of hit this inflection point, going down, and then up again. So we kind of have multiple places. We have going down until here. We have another down right here. But then going up, I'll kind of use green for up. Green, we're walking uphill here, and we're walking uphill there. So where are we walking downhill? This is the interval part. So we have been walking downhill on this graph. This graph continues on and on and on forever. There's an implied arrow right here. So that graph has been going down from negative infinity all the way down to, what would that be? Negative like 1.5. This is the x values. So we're always looking at the x values. Okay, where are we going up? We're going up from that same negative 1.5 until I would call that value of 1. Okay, and then, okay, we're going downhill again from this value of 1 to this value of 2. It's a slight downhill, we get a little bit of a break. And then back to uphill at that value of 2, and then we are forever walking back uphill to positive infinity. So positive and negative intervals, we want to think about reading that graph. Okay, and then we'll look at relative maxima. Maxima is the plural word for maximums and minimums. So if I were to look at this graph, I have a absolute minimum right here. I call it absolute because that is the very, very bottom of the graph. I kind of also, though, have a minimum right here. It's kind of a low hump, right? So that's why we say relative. It's relative to kind of everything else in the graph. And then I have a little bit of a hump right here, and that's going to be my relative maximum. So I have a max here, I have a minimum here, and then I have a minimum here. We're going to write those as coordinate pairs, and then that's how we identify the relative maxima. And then now we're going to look at end behavior. I will say end behavior as a concept is quite simple, but it is mathematically, the way that it's written is kind of challenging. So I have kind of two arms of this graph, right? So on this side, I'm going to call this the left side of the graph, and then we have the right side of the graph, right? Now, what's happening to my graph on both the left and the right? Well, on the left-hand side, I can see that the end of the graph is continuing to go up. On the right-hand side, this end of the graph is continuing to go up. This is, in essence, what is the end behavior. We're describing kind of those branches, those arms. Left side go up, right side go up. Now, mathematically, what we do is we describe, in mathematical terms, that concept of left and right and up and up. So let's look at the left. Since we're describing left, we're thinking about horizontal. So what is the number that is like the most left number that there is? That's negative infinity. And we want to say, hey, x, as we move further and further left. So this would read x approaches negative infinity. So as we move further and further left, as x approaches negative infinity. Okay, and then the right, we're going to say x approaches positive infinity. Positive because like that's the most positive right-handed, right-sided number that we can think of. So that's how we're always going to start. We start by describing which side of the graph we're looking at. And then now we're going to jump to what is the graph actually doing? Well, in this case, our graph is going up. Up, we're thinking about y's. Y is going up. So what's the most up positive number that we can think of? It's going up towards infinity. And then same thing here. Y is also going up. So it's going up towards positive infinity. So that is how I would describe the end behaviors. So coming back and looking here, we can see it described right here. This is how I would read this. As x approaches negative infinity. So as x is moving to the left, my function, f of x, approaches infinity. Oh, that's my function, so my y's positive infinity, so that has to be going up. As x approaches infinity, positive infinity, okay, so now we're talking about the right-hand side. F of x approaches positive infinity, so we're going up as well. So again, I think end behavior as a concept, pretty simple, straightforward to grasp, but the way that it is written mathematically, yep, a little wackadoo. Okay, let's look at another one. Here we are looking again at positive intervals, negative intervals, relative maximum, end behavior. So hopefully visualizing that graph going in, we can see end behaviors. We're going down to the left, down to the right. So I would say as x is moving further left, which is negative infinity, my function is approaching negative infinity. Left, down. On the right-hand side, so that would be as x approaches positive infinity, my function is going down, so most negative number that I can think of, which is negative infinity. Okay, and then we have relative maximums. Absolute maximum, kind of another maximum here. So here we have maximums. I would find those coordinates. And then I have a minimum right here. Another great thing about Desmos, my friends, it tells me those coordinates. So coordinate for my minimum, coordinate for my maximum, coordinate for my maximum. And then for intervals, go on your walkabout. Walk up your graph, walk down your graph. So here we have relative maximum, positive intervals. Where are we walking up? We would walk up from -3 to a -1, and then another little section from 0 to 3. And then there's a lot of walking downhill in this graph. And then here we have the end behavior. So I hope this clarifies a lot for that checkpoint 16. This is probably a longer video, but I hope that it was helpful.